This is our second part of Note 6.4. Taking a look at an AP exam question from 2010. This is a BC question, has some BC material in it. You can see that it starts off by saying we have this differential equation, and then it says that y is defined as just some function f of x, and we know from the initial conditions, or they give us an initial condition of f of 1 is 0. So let's go ahead and take a look at this one. The first one says, hey, let's use Euler's method to solve this. We're going to skip that and jump to the one that applies to this unit, and that's part B. So first of all, we know a little bit about f of x. We know that it is a differential equation, so it is differentiable. Just the fact that it's shown here, which means this is a continuous function, and that we're given this initial condition of f of 1 equals 0. Because we know it's continuous and f of 1 equals 0, we can state, and again, we need those two conditions in order to apply this, we can state that the limit as x goes to 1 of f of x equals 0. And I would suggest that you would probably add in there the fact that you know f of x is differentiable at x equals 1, and therefore continuous, because us at x equals 1, because if it wasn't continuous, if this was just a random point, so to speak, on the graph, then our limit wouldn't apply. If you remember from our limit rules, that the limit from the left must equal the limit to the right, and if you're continuous, the limit from the left will always equal the limit to the right. Okay, so that's probably something that you'll need to state so that you can definitively say the limit as x goes to 1 of f of x equals 0, as shown here on that. And then in our denominator, let's evaluate that. The limit as x goes to 1 of x cubed minus 1, of course, is going to be 0. Okay? So we've got that out of the way, and that's probably going to be part of a point that you're going to need to do, because remember what we said here, if we have this case of 0 divided by 0, we can say something like this, therefore, this limit that we're evaluating, the limit as x goes to 1 of f of x divided by x cubed minus 1 is indeterminate. And L'Hopital applies. Okay. So all of this would be necessary for us to get a point on the justification side of this. All right. So let's go ahead and apply L'Hopital. That means the limit as x goes to 1. We still haven't taken that. L'Hopital says this will be f prime of x, and then our denominator will be 3x squared. Derivative of x cubed is 3x squared. Derivative of 1 is 0. Okay? And then what we can do is just go ahead and do some algebra here. We're just going to evaluate this by substituting in 1. F prime of 1 divided by x of 1 quantity squared. Okay? We do need to go back up here and look at this in order to be able to evaluate this, to find out what in the world is f of 1. Okay? So let's go back up here. We know that y equals f of x, so if we are evaluating f prime of x, that's just got to equal dy dx, this guy up here. So f prime of x would be 1 minus, y, not 1, that's when x equals that. Okay? But think about it. Y is just f of x, so when x equals 1, this will be y of 1, which of course is 0. So that means this is just going to be 0. F prime at 1 will be 1 minus 0, or 1. This just is going to be 1 over 3 times 1 squared, or 1/3. Okay. That's showing all the work that leads to our answer. And that's going to be worth 2 points. Okay. Now, while we're at it, let's just go ahead and do this one. It does involve a little bit of separation of variables, a key that you've learned before, but I do want to emphasize so that we can make sure when it does come to the exam that we're very, very good at this. So remember, we have a differential equation, dy dx equals 1 minus y. Okay? Separation of variables is required here. What we can do is take and divide both sides by this and multiply both sides by this. The result will be the integral of 1 over 1 minus y dy equals dx. Okay? Or it would be this, and then of course we're going to evaluate the integrals in order to solve this. Okay? And this is real simple. On the left-hand side, this is going to be an x plus c. Derivative of 1 is x. Over here, we do have something we've seen from our last unit, and that is remember when we had f prime of x over f of x dx? This is simply just going to be the natural log of the absolute value of f of x plus c. Okay, now we're pretty close to this. Our reverse chain rule is going to require us to have a negative out in front of this, but this would just be negative natural log of 1, or the absolute value of 1 minus y, and that's going to be equal to x plus c. Okay. It does say find the particular solution for the initial conditions f of 1 equals 0. So remember, f of 1 equals 0, that means x equals 1 and y equals 0. We're just going to substitute that in here in order to solve for our c. This will be negative natural log of 1 minus 0 equals 1 plus c. Well, of course, this is just going to be 0, and c would have to be negative 1. So we can continue on by saying that the opposite of the natural log of the absolute value of 1 minus y equals equals x minus 1. That's from this. Arranging this by getting rid of that negative would give us the natural log of the absolute value of 1 minus y equals let's just switch these around to 1 minus x, since both of those signs changed with this. Of course, to get rid of natural log, we have to take this, raise it to the power of e, which will bring this down to the absolute value of 1 minus y equals e to the quantity of 1 minus x. Okay. Then, looking at this, what we can do is go ahead and this, of course, is just going to be a positive number. So if we subtract 1 from it, kind of running out of room, and then multiply by negative 1, this will be 1 minus e to the 1 minus x. And I guess I could rewrite it as f of x equals 1 minus e to the 1 minus x. since that's what it was asking for, that particular solution to it, or either one of those forms, I'm sure would be okay if we wrote it like that. Okay? So that is a nice little example of something you did before, and then I want to reiterate to you. I'm going to show you the grading on this one to make sure you understand. Okay? On the AP exam, this question is worth 5 out of 10 points. The first point is separating the variables. That's what we did here. And we got the y's on one side and the x's on the other. Okay. Then, down here, because there are 3 of you who I've noticed from your work are a minimalist. You're not going to write anything down because I guess you're much smarter than the grader. Well, the grader is not going to think you're that much smarter than them. Okay? If you don't separate the variables, you have everything written down from here on down. You have that solution. 0 points. Again, if you don't separate the variables, if you think that's beneath you, well, your score is going to be beneath what you expect. Okay? Next, some of you are forgetting these. You're saying, hey, I can put the plus C in any time I want. Okay? And you'll see, once you get to here, okay, antiderivatives, boom, boom, okay, those are shown there. You get 1 point for the constant of integration. Oh, wait a second. Notice, if you didn't put the C here at the very first spot, you just kind of did your own little way of doing calculus. Okay, wonderful. You got to the solution here. You got this. But as far as AP is concerned, as soon as you wrote this down without the plus C, from there on, no credit. Again, if they don't see the plus C, as soon as you take this antiderivative, they are not going to look at anything from here down. They're done grading it. Okay? So, 2 common little things that I've noticed on some of you that you're doing, and it's just, be frank, it's just laziness. Okay? Separate your variables. Put your plus C's as soon as you take an antiderivative. Don't do a little thing over here and a little thing over there and then bring them together. Okay? So hopefully I've made my point on those. And let's quickly take a look at our next page. And it's giving us a little bit of relief. There will be some problems that you're going to have on the AP exam that are multiple choice. And we can probably get to them a lot quicker than having to apply a full-blown L'Hopital. So let's talk about some growth rates here. When comparing growth rates, we only consider 2 types of functions, as y goes to infinity, x goes to infinity, or y becomes and remains positive as x goes to infinity. So let's think about this. If we have this function e to the x, it gets big really, really fast. It's going to grow rapidly. For example, at x is 1 centimeter to the right, the value of the function e to the x is just going to be a little bit more than 3 centimeters tall. If we go 6 centimeters to the right, we're already up to 403 centimeters, okay? Or about 4 meters. If we go 10 centimeters, just 10 centimeters to the right, we're going to be up 22,000 centimeters, or 220 meters. If we go 43, just 43 centimeters to the right, okay, less than half of a meter stick, we are this tall. To put that in perspective, it would take us 5 light years to travel that far. So again, half this e to the x function. If you graph this on an axis and you go to the right less than half of a meter stick, you're going to be 5 light years tall. Pretty crazy. Okay? Now let's think about our natural log of x. Okay? It's very slow. This function will go to infinity as x gets bigger and bigger. Okay? And remember the relationship. They are inverse of each other. So, with that being said, if you were to graph this natural log of x function and start going to the right and going to the right and going to the right and going to the right, and you go to the right a distance that light would take 5 years to travel, the natural log of x function wouldn't even be a half of a meter tall. It would be at 43 centimeters tall. Okay? So, hopefully that gives you a perspective of a function that grows slowly and a function that grows rapidly. Okay? So, if we have a faster growing function up here in the numerator than in our denominator, this one being the slower one, then it's going to act like an infinity divided by some number, or it's going to go to infinity. If we look at that function, we say, hey, wait a second here. The fast function is the one that is in the denominator this time. Okay, it's f is the one that's going slower. The faster one is this one down here, our g of x function. Then it's going to act like some number divided by infinity, and this one's going to go to 0. If they grow at the same rate, we're always going to go to some number where it's going to be a number that's greater than 0, but of course less than infinity. So let's think about this. If I have these two and I want to evaluate them to say, hey, which one grows faster than the other, what I can do is just evaluate the limit as x goes to infinity of e to the x divided by x squared. Now, I won't go through all the process that's required to apply L'Hopital, but think about this. Those are both infinity divided by infinity, so it would be the same thing as the limit as x goes to infinity of the derivative of the numerator divided by the derivative of the denominator. Still infinity divided by infinity. The limit as x goes to infinity of the numerator is e to the x. The denominator is 2, which we know goes to infinity. Since the limit is going to infinity of this rational function, we know that the denominator has to be the one that grows faster. And let's do the same thing here with the next one. Again, we can think about these, but just think of them in relationship L'Hopital. We have an infinity in the natural log of x going to infinity, and of course x, and just one case of L'Hopital, we would get a 1 over x divided by 1, which of course is giving us 0. Now, since we're of this form right here, then the only way this could go to infinity is if the faster growing one, the g of x, is in the denominator. So, again, this is a quick little example of, hey, if I'm comparing to which one grows faster, which one goes slower, I just write it as a rational function and look to see if I go to infinity or 0. If we go to infinity, numerator faster. If we go to 0, denominator is faster. Okay? So let's take a look here at these. In this case, we would have the limit as x goes to infinity of 2x divided by 3 to the x. These are both infinity divided by infinity, but you'll notice here, as I start applying L'Hopital, that really doesn't help us because we still get a 2 to the x and a 2 to the x, or 3 to the x. Okay? But apply some of our exponent rules here. This would be the same thing as taking 2/3 all to the power of x. Okay? And then if you remember, this is going to be a function that keeps getting smaller and smaller because as x gets bigger, say 1, we have 2/3, and remember squared, we're going to take 2/3 of that. Cubed, we'll take 2/3, and then 2/3, and 2/3. So we keep getting smaller and smaller and smaller. This is going to go to 0. Look up above. When we have a rational function that goes to 0, it is our denominator that is the faster of these. Boom. Let's take a look at the next one. In this case, we've got the log base 2 of x and the log base 3 of x. So let's evaluate the limit as x goes to infinity. And remember, with our calculus, these logs aren't so great as far as trying to take derivatives of them and evaluating them. So let's apply our log law and write this as the natural log of x divided by the natural log of 2. That's the same thing as this. They're the exact same thing. I didn't take any derivatives. I didn't evaluate any limits. I just used my log law. Same reason as this would be the natural log of x divided by the natural log of 3. This guy right here. Okay. Now, applying our algebra, natural log of x divided by the natural log of x is going to be a 1. And then this one down here is in the denominator. And we're dividing that, which would be the same thing as multiplying by the reciprocal. The result's going to give us something, the limit as x goes to infinity of this one would just be the natural log of 3 divided by the natural log of 2, which is just going to be the natural log of 3 divided by the natural log of 2. They are a number, and that number is, of course, greater than 0 and less than infinity. Therefore, both of these grow at the exact same rate. Both of those functions grow at the same rate. Let's take a look at our next ones. Yeah. And again, we're going to quickly take a look at these and consider them as if we were applying the limit as x goes to infinity of e to the cosine of x divided by e to the x. Looking at this, and we're kind of in that same boat of L'Hopital isn't really helping me here. Okay. But let's think about this. Cosine. The cosine of x is always going to be greater than -1 and less than 1. So it doesn't matter how big x gets. This thing's not going to, the most it's going to be is x to the first power, or excuse me, e to the first power, a little bit more than 2.7, or e to the negative first power, okay? Remember, that's just going to be a little bit more than 0.1. And e to the x, well, as that goes to infinity, this is going to go really, really big. So this is going to go to 0, which means this guy is the fastest growing of the two. Let's take a look at our next one. In this one, we can think of this as the limit as x goes to infinity of the square root of 1 plus x to the 4th, all divided by x squared. And yeah, think about this. As x gets bigger and bigger and bigger, does it matter that you're adding 1 to this? So as x gets out to a million, a billion, and so on, the 1's not going to matter. It's just going to be x to the 4th power. The square root of that is going to be in x squared, which means this is going to go to 1, which means this is another one that grows at the same rate. Okay. Let's take a look at our next one. This one would be the limit as x goes to infinity of our 2 to the x divided by x squared. Now this one, I would say, yeah, you know what? If we do apply L'Hopital, notice how the denominator would be 2x and then 2. So it's pretty obvious that this guy right here is going to be the faster growing of those. Okay. Next one, we've got the limit as x goes to infinity of 0.0, a bunch of zeros, a 1, and then x to the 5th power, x times x times x times x times x, all divided by 5 times x to the 4th, x times x times x times x. And quickly you can see we've got an x in the numerator after we simplify this, and regardless of how many zeros are on here, if this is going to infinity, even though we're dividing it by 5, and this is a really, really small number, infinity is so much bigger than that, so it should be pretty obvious that no matter what that coefficient is, this is the faster growing of those. Yeah. So hopefully you've enjoyed these notes. They are 2 parts, and you just completed the second part. Have a good time doing your homework tonight, and we'll see you tomorrow.